All right, let's get started. So good morning, everybody. I hope you are doing well. Just a couple quick announcements. So as a reminder, there's going to be our Chapter 4 quiz, which will happen on Monday. Again, it'll open at 12:01 a.m. and it'll be open until 11:59 p.m. You'll have to find a 1-hour time to take that chapter quiz. And this afternoon, William will be doing a review on the Chapter 4 review that is posted on Moodle. So if you would like to attend that, you can. Otherwise, the link to the recording will be posted at some point tomorrow. So today we're going to be moving into Chapter 5. So the stuff that we do today will not be on Monday's quiz. This is the beginning of our last chapter that we will cover for this course as we sort of move through. So I want to give you just a brief 1-minute overview of what Chapter 5 is going to be teaching us, so you keep that sort of in your mind as we go through. So as you know, chapters 1 and 2 were helping us build up to understand what derivatives are, how they work, why we might need them. Chapter 3, we looked at the computational side of taking various derivatives. Chapter 4, we applied derivatives to all sorts of scenarios to find things like local maxes, local mins, inflection points. And now Chapter 5 takes an alternative approach and says, okay, well, what if we have information about the derivative? What will that tell us about the original function? And we've already done this to a small extent through the relationships of things like when the derivative is positive, the original function is increasing, things like that. But we're going to sort of formalize a little bit more what kind of information we can know and understand by having a derivative to work with. Okay, so that's sort of the big picture of what Chapter 5 is going to do. So I'm going to go ahead and switch over to the doc cam. Okay. And so when we start Chapter 5, we start what's called distance and accumulated change. So we start with what we know about a very common derivative that shows up in our lives, and we use that to sort of explore how we might extend that to other types of derivatives. So we start with this idea that distance equals velocity times time. And so if you think about, you know, the common rate of change we know, we often refer to driving. So if you're going 60 miles per hour, that is 60 miles times 1 hour, 60 miles per hour, that gives you a distance. So after an hour, you've gone 60 miles. So that's sort of the example we're going to think about as we go through the first couple of examples, okay? So I want you to think about this. If you were going to travel 40 miles an hour for 3 hours, how far did you travel? Okay, so take like 20 seconds to jot down what you think is going to happen there. Okay. So let's figure out how we can write this out using units. So 40 miles per hour. So I'm going to write it as m/h, miles per hour. And we travel for 3 hours. So if we multiply those together, we can see that the hours units cancel. And I'm left with 120 miles. So if I take the velocity, the rate at which I'm traveling, 40 miles per hour, and multiply it by the time that I go that rate, it will tell me the total distance traveled. Now, one of the things that we need to recognize here is that this 40 miles per hour is a derivative, okay? Velocity is the derivative of position. And when we talk about 120 miles, that is giving us information about the position. Okay, it's how much the position changed. So we started with the derivative and we used it to find information about the original function. Okay, how can we represent this graphically? So this might be a little bit new. Okay, but what we can do in this situation is we can graph our rate versus our time. And in this scenario, our rate is 40 miles per hour. So we are going to graph 40 as our rate. Now, since that rate is constant, we have to graph a horizontal line that covers 3 hours, right? So 1, 2, 3 hours. So 40 miles an hour for 3 hours. So if we were to look at the area underneath this particular function, we could use geometry to figure out the area of this rectangle, right? So 40 times 3 is 120. That's what we got up here. So what that tells me is that if I am able to graph my rate over the period of time, that the area underneath that line represents my change in the original function, which is 120 miles. Okay. So how do we extend this? So example 1, I want you to think about this and I want you to try to compute this algebraically and then see if you can draw a similar graph to compute this graphically. So the example says, if you were to travel 20 miles an hour for 3 hours and then 50 miles an hour for 4 hours, how far did you travel? Okay, compute this algebraically and graphically. So I want you to take 2 minutes. I want you to think about, now we have 2 legs of this trip. How do we get the total distance traveled? And how do we draw a picture to represent that? So take 2 minutes, try out what you think might look like on a graph, and then we'll go through it together. Okay, take about 30 more seconds. All right. So let's do this algebraically first, and then we'll look at how we might set this up graphically. So there's 2 different rates in this problem, and each one we connect to a specific amount of time we are at that rate. So for the first leg of our trip, we're going 20 miles per hour for 3 hours. So if we multiply those together, we get 60 miles for the first leg of our trip. And then we're going 50 miles an hour for 4 hours. So that's the second leg of our trip. Again, we can cancel out the hours units. And we get 200 miles for the second leg of our trip. So together, we traveled 260 miles. Okay, so we can take each rate and multiply the amount of time that we go that rate, and then add up all the individual pieces. Now, What about graphically? What's that going to look like? Turns out there's actually a couple different ways we can do this. Okay. So we know that we have a constant rate of 20 for 3 hours, and that happens first, right? So let's go 1, 2, 3. Okay, so 20 miles an hour for 3 hours. And again, the area underneath this creates a rectangle. And if we find that area, we get that 60 that we found algebraically. And then after that, we have the second leg of our trip where we go 50 miles an hour for 4 hours. So if we start at hour 3 and we go for 4 hours, that goes out to hour 7. So here, and again, if we were to find the area under this curve, we have 50 miles an hour for 4 hours. That gives this leg of the trip 200 miles. So graphically, what we would need to do is we would need to add up these areas again, and we would still get 260 miles. Okay, so that's what that would look like if we were to graph it. And again, you can do this algebraically or you can graph it, but we're going to practice doing both, because what's going to happen eventually is we'll find that we can no longer compute things algebraically, and we want to be able to rely on the picture. Okay, so let's look at another quick example here that is not about driving. So we can see that this applies to all sorts of different rates. So suppose a population is growing at a rate of 2,000 people per year for 3 years, and then 3,000 people per year for 4 years. What is the total change in population over those 7 years? So again, I'd like you to figure this out algebraically, and I would like you to draw a picture representing what's happening with this change. Okay, so take about 2 minutes, see what you can sketch out, see what you can figure out, and then we'll go through it together. Okay, take about 30 more seconds. All right, so again, we'll start with the algebra. It doesn't matter which one you start with, you'll get the same result. But algebraically, our first rate is 2,000 people per year, and our first time is 3 years. So I'm going to write 2,000 people per year. I'm just going to abbreviate the units here, people per year, times 3 years. Again, we're going to see that the years cancel. and we get 6,000 people. So our population has changed by 6,000 people during the first 3 years, but then we have a second rate. So then we get even more people. So 3,000 people per year for the next 4 years. Again, the years are going to cancel. We're going to get 12,000 people. Okay. And since these happened, both of them, we need to add that up. So 6,000 plus 12,000 gives me 18,000 people. Okay. Now, I want to be clear that this 18,000 people is how much the population changed. It's not the size of the population. We have no idea how big the population is. It could have been 1 million people that changed by growing 18,000 people. It could have been 5,000 people. We don't know what the initial population is. And this 18,000 represents how much it has changed over those 7 years. It doesn't represent the actual population. It represents the change in population. Okay. So now, if we were to graph this, again, so we start with our rate versus our time. Our first rate is 2,000, so I'll throw that on the axis for 3 years. 1, 2, 3. Right, so again, area under the curve. Right, 2,000 times 3 gives us our 6,000. And then after that, we have 3,000 people per year for the next 4 years. So up here. So again, the area under the curve or the line here, we have 3,000 times 4. That gives us that 12,000 people. So again, we would add the 6,000 plus the 12,000, and we would get a total of 18,000. Okay, so far, all of the rates that we have been considering have been constant. So that means that it's the same rate for some amount of time. We're not talking about a rate that's varying. So the next thing we have to do is we have to consider how we might solve a problem if the rate is not constant. Okay. So we're going to look at this next example, example 3. So suppose the rate at which a skateboard is moving over a 60-second interval can be written as f of t equals 3t, with f of t in feet per second and time t in seconds. What is the total distance traveled by the skateboard over the first 10 seconds? So this is obviously a little bit different, and we have to think about how we might use this rate to figure out and answer the question. Okay, so I'm going to have you try this, and I want you to think about what it might look like if you were to graph this versus the ones we've previously done, or if you think you have a good way to do it algebraically. But I'm going to give you 2 minutes to try to work it out, see what you can figure out, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so this is a little tricky because before we were able to multiply our rate times our time. And our rate here is 3t. If we were to multiply 3t times 60, we would still have a variable in our answer, right? We'd still have the t, we would just have 180t. We could think about trying to plug 60 into f of t, but that also wouldn't be accurate because that would just give us the rate at time equals 60 seconds, which is different than the rate at time equals 0 seconds. So the way that we need to approach this, okay, is to think about what the picture is going to look like. So remember, we're considering the rate versus the time. Now, before our rate was constant, which meant we had a horizontal line. Now our rate is 3t. Well, 3t is a linear function that goes through at the origin, right? When time is 0, then the rate is 0. We are interested in what's happening over the first 10 seconds. Okay, so we have time equals 10 here. So if we follow what we did before and we look for area under the curve or under the line, it turns out that instead of a rectangle, we end up with a triangle. And triangles are also a geometric shape that we can work with. So as a reminder, the area of a triangle is 1/2 base times height. Okay. So if we were to consider that, we would have 1/2. Now my base goes from 0 to 10. So I have my base is 10, but then I have to multiply by the height. And so the question is, do I know this particular height? And the answer is yes, right? Because this particular height is the y value if I plug a 10 into my function. So times 10 is going to give me a height of 30. Okay. Now, in addition to computing this number, I want to make sure that the units all work themselves out to make sure I've picked the right types of numbers. So the half doesn't have any units because that was part of the triangle formula. 10 is 10 seconds, right? That was our time. And the 30 came from this rate. So when I plugged a 10 in here, this was in feet per second. So at time equals 10, the skateboard was moving 30 feet per second. So when I multiply this, the seconds units are going to cancel, and I'm going to be left with feet. So here, half times 10 times 30 gives me 150 feet, which makes sense because we're asking for the distance traveled during that 10 seconds. So during the 10 seconds, that skateboard traveled 150. So what we're trying to do now is think about how we can take functions that are not constant, so functions like 3t, things of other functions we'll get to later, and how we might be able to use the picture of them to help us understand how much the original function changes. And that relationship is that it's the area underneath the function and between the independent axis that gives us how much the original function changes. So if our rate is constant, we're thinking about rectangles. If we have something that is linear, now we're talking about triangles. As you can imagine, if we had something that, was parabolic, so t squared, t cubed, all of a sudden our geometric shapes are no longer adequate, right? So we don't have a good way to come up with a geometric situation where we might have something super curved, right? We're not going to be doing arcs or anything like that. So our next step is to say, okay, well, what happens if we have something that's not linear, right? Either horizontally linear or in a situation like this where we have this line, okay? So we're going to use a table and we're going to consider this question so we can sort of demonstrate and think about how we might deal with other types of functions. So suppose we measure the velocity in feet per second of a bicyclist racing down a flat road, and we're able to measure their velocity every 2 seconds. Okay, so someone is riding down the road, every 2 seconds, we're able to capture their velocity and record it in a table. So here at time equals 0 is right when they're starting. After 2 seconds, they're going 5 feet per second. After 4 seconds, they're going 7 feet per second. And then after 10 seconds, they're going 22 feet per second. Okay. The question is, how can we best estimate the total distance traveled over the 10-second interval, right? So think about what we were doing before when we talked about those sort of legs of the trip, right? We were going 50 miles an hour for 4 hours. So what we can't do is we can't multiply just straight down velocity times time. Because if we were to multiply 10 times 22, that would mean that we were going 22 feet per second for 10 seconds, which is different than going 22 feet per second at time equals 10, right? So we have to think of some creative ways to sort of figure out what might be going on. And the way that we approach this is we consider each of these little time intervals. Okay, so this is 2 seconds. This is 2 seconds. This is 2 seconds. This is 2 seconds. And this is 2 seconds, right? So from time equals 0 to time equals 2. Sort of our first interval here. And then from time equals 2 to time equals 4, time equals 4, time equals 6, time equals 6 to time equals 8, and time equals 8 to time equals 10. So we've broken these down into these 2-second intervals that we're going to evaluate. And the reason that we're breaking these down is because for each interval, we are going to assume a constant rate, because that is something we know how to work with from our first couple of examples. Now, I want you to notice that in this table, every time interval is the same, right? So we're counting by 2s here. That's not a coincidence, okay? So whenever you're doing this type of work, we need to break it down into equal intervals. So here, my time interval is 2 seconds. And one of the notations we're going to talk about in a few minutes is that we notate this by calling that delta t. So my delta t here is 2. We're counting every 2 seconds. Okay, so during this 2-second interval, I have 2 different rates, right? And remember, distance is rate times time. So we know the time is 2 seconds. But what about the rate? We have a rate of 0 and we have a rate of 5, okay? So what we can do is we can look for each time interval and consistently pick a rate based on position. So what does that mean? So for the first 2 seconds, from time equals 0 to time equals 2, I'm going to pick the rate on the left. Okay, so for the first 2 seconds, I'm going to assume that I was going 0 for those 2 seconds. So that means that my rate times time will be 0 times 2. Okay, from time equals 2 to time equals 4, I'm going to pick the rate on the left. So now my rate is 5 times time, again, another 2 seconds. From time equals 4 to time equals 6, I pick the rate on the left. I'm being consistent in how I'm picking this. 7 times 2. From time 6 to time 8, I pick the rate on the left, which is 10. 10 times 2. And then time 8 to time 10, I pick the rate on the left, which is 15 times 2. Now, as we did before, we want to add up all of these values, right? So this is 2, this is 10, this is 14, this is 20, this is 30. If I were to add these all up, 74, 76. Oh no, this is 0, you guys. 0 times 2 is 0. So that's going to give me 74, right? If I add all of these up, I'm going to get 74 feet, okay? And so I found my approximation for each 2-second interval. Now, if this was an important race and you were this bicyclist, right? And this is how I approximated your total distance traveled, you would probably be pretty mad, right? Because I didn't even use the 22, right? Since I always pick the rate on the left, I never used your best rate, okay? So this type of approximation that I just did is called a left-hand approximation or estimation. And we usually notate it LHE. Now, if I can do a left-hand estimation, there's also then a right-hand estimation, right? So for a right-hand estimation, I'm going to do the same exact thing, except for each 2-second interval, I'm going to pick the rate on the right. So from time equals 0 to time equals 2, if I pick the rate on the right, now I'm going to pick 5 times 2, rate times time. From time equals 2 to time equals 4, I pick the one on the right. I have 7 times 2. From time equals 4 to time equals 6, I pick the rate on the right. So I have 10 times 2. From time 6 to time 8, I pick the rate on the right. 15 times 2. And then finally, from time 8 to time 10, I pick the rate on the right. 22 times 2. So again, I need to add up all these sort of interval distances. So we have 10, 14, 20, 30, and 44. If I add those all up, I get 118 feet. And this was a right-hand estimate. Okay. So what do I do with this information, right? I have this right-hand estimate. I have this left-hand estimate. When you do this type of work, what I know, okay, mathematically, what's going to happen is that my actual total distance traveled, which is my change in position, so I'm just going to call it my distance, has to be between the lower estimate, 74, and the upper estimate, 118. So those give me bounds of where the actual estimate needs to be. And I also have what's called a best estimate, which is what I get if I average 74 and 118, right? So again, my best estimate is a guess based on the information I have. And if I get different information, it may change my guess. So my best estimate, I'm going to average 74 plus 118 divided by 2, and that's going to give me 96. So what does this look like, right? How does this sort of play in with this idea that we should be graphing what we are approximating? Let me grab a piece of paper here. Okay. So if I were to draw a picture of this approximation, this is my time, This is my rate. Remember, rate versus time. When I do a left-hand approximation, okay, so 2, 4, 6, 8, 10. Okay, so each time interval is 2 seconds long. When I do a left-hand approximation, I'm going to do that first. I'm always picking the rate on the left. So I picked 0, right? So this is part of my left-hand approximation. So that means from time equals 0 to time equals 2, I'm right on the axis. So that's kind of boring. From time 2 to time 4, at that point, my rate jumps up to 5. So that means that I have something that is constant at 5 from time 2 to time 4. From time 4 to time 6, I was at 7. So I'm just going to count by 5s to help give us a visual here. So let's say 7 is here. Time 6 to time 8, I was at 10. So that's up here. And time 8 to time 10, I was at 15, which is up here. Okay, so remember, there is another rectangle here that has 0 area. So we found the area of each of these blocks. And when we do a left-hand approximation, what is happening is we are connecting sort of the left-hand sides of each of these rectangles to try to get an approximation of what our function actually looks like. Okay, so my left-hand approximation is creating these little constants so that I have these rectangles. Okay, so this is a left-hand estimation. Now, when I did a right-hand estimation, for the first 2 seconds, I assumed that the rate was 5. So that means I had something like this. And then for the next 2 seconds, I assumed the rate was 7. And then from time 4 to time 6, I assumed it was 10. And then time 6 to time 8, I assumed it was 15. And then from 8 to 10, I assumed it was 22. So I have to add some more numbers here so I can get up to 22. Okay. And so when you do a right-hand estimation, the right-hand corners of each of your blocks forms your sort of approximation of whatever this function is. So what I want to point out here is that when we did this particular example, the left-hand estimation is what's called an underestimation for this example, because when we did the left-hand estimation, we didn't get all of this area under the curve. There was still some missing, right? We were below the curve, whereas our right-hand estimation was an overestimation because it gave us more area than was under the curve. Now, it's important to note that whether your left-hand estimation is an overestimate or underestimate depends on the function. You would need to do both a left and a right to see which number was bigger. And the bigger one is your overestimation, and the smaller number is your underestimation. And again, the idea is that we are trying to get the exact area under this function, but it's curved, right? So right now, this is sort of the best that we have. So I want to introduce one other, or I guess 2 other pieces of notation that we're going to see. So we said that delta t equals 2 because we're counting by 2s, right? So this is delta t, this is delta t. These are all 2, right? Another thing that is going to be important to us is n. N is the number of intervals that we are using to approximate. So on our picture, that translates to the number of rectangles. On our algebraic computations here, it's the number of intervals. So here is 1, 2, 3, 4, 5. There's 5 intervals. Similarly, right, we have 1, 2, 3, 4, 5 rectangles. So here my n is 5, okay? And then I also want to bring in this idea of endpoints. So A is usually what we call our left endpoint, which here is 0. And B is what we call our right endpoint. Okay, which here is 10. So if we adjust different things in our approximation, if we made delta t smaller, that would make n bigger, right? So if we counted by ones instead of twos, we would then have 10 rectangles instead of 5. If delta t was 5, if we were counting by 5s, there would only be 2 rectangles. So all of these types of variables are related, and we're going to talk about those relationships in a few minutes, but I want to start pointing out what they look like on the pictures that we're drawing. Okay, so we have this idea of a left and a right-hand estimate, and from that, that gives us bounds for where our actual total distance traveled is, the actual area under the curve. So let me move this over here. So far, in terms of our terminology, we have a left-hand estimate. When we do a left-hand estimate, we assume the rate on the left is constant. So we're always picking between 2 rates, and we pick the one on the left. If we do a right-hand estimate, we assume the rate on the right is constant. The overestimate, we compare the left and the right estimates, and we choose the bigger one. That's your overestimate. Your underestimate, we compare the left and the right estimates, and we choose the smaller one. Okay, and then so far, we know that delta t is our time interval that we're using for our approximation, so how we're counting in our independent variable. N is the number of rectangles that we're using to estimate, and A and B are the start and end points, which are defined by the independent variables and values. Okay, so let's consider the example we just looked at. And now let's assume that during the same bicycle race, we actually were able to measure every 1 second instead of every 2 seconds, right? So notice that at 0, 2, 4, 6, 8, and 10, those values are the same as our last example. The difference here is that now we know what's happening at 1, 3, 5, 7, and 9. We just have additional information. And so we're trying to figure out, is it better to count every 1 second? Is it worse? Do we want our delta t to be bigger? Do we want our delta t to be smaller? So the way we do this is by, again, doing a left and a right-hand estimate and finding the best estimate and comparing that to when we had delta t equals 2. So now delta t equals 1. So I'm going to have you try this. Again, we're going to do rate times time for each interval. So from time 0 to time 1, that's 1 interval. We're going to pick the rate on the left. And from time 1 to time 2, you pick the rate on the left. So everything's going to be multiplied by a 1 here. And then you'll do the right-hand approximation. Okay, and then we'll compare. So if you still have time after you've done a left and right-hand approximation, you can also jot down what is delta t, what is n, what is a, and what is b. So those are the other sort of key pieces of information. So I'm going to give you about 3 minutes just because there's a lot of values here. Find the left and the right. If you still have time, find these values, and then we'll go through it together. Okay, take about 30 more seconds. All right. So when we do our calculation on this set of data, which again is the same as the other one, but now we have more information, our delta t here is equal to 1. So now we're counting by 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for each 1 second interval, we're going to pick the rate on the left when we do a left-hand approximation. So first we pick 0, then 3, then 5, 6, 7, 8, 9, 10, 12, 15, and 18. So notice when we do a left-hand approximation, we don't use the rightmost rate. Okay? So when we add those all up, I get 84 feet. Now, when we do a right-hand approximation, we're going to do the same thing, only now we're going to be picking the rate on the right for each calculation. Oops, so we have 3 times 1 plus 5 times 1 plus 6 times 1 plus 7 times 1 plus 8 times 1 plus 10 times 1 plus 12 times 1 plus 15 times 1 plus 18 times 1 plus 22 times 1. So notice that when you do a right-hand approximation, you don't use the leftmost rate, right? So when we add those up, we get 106. So this is different than what we got before. So let's go here for a second. Before, we knew that our total distance had to be between 74 and 118. We then changed our delta t to 1, and now we know our total distance has to be between 84 and 106. So this interval, this new interval, is smaller than the old interval, right? So this is a better approximation because there's less variance. Our interval is smaller. So what that tells me is that the smaller my delta t is, the better my approximation. So the last step here to sort of answer this particular question is we need to find the best estimate. So we would add up the 84 and the 106 and divide by 2. I just did that quickly, and we get 95. So that's different than our best estimate from before. So again, by making delta t smaller, our interval where our actual area needed to be shrinks, which makes it a better estimate than what we had before. Okay, so the other thing I want to point out that has changed here is our n. So n is the number of intervals we're using. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there were 10 intervals that we used, and it's not a coincidence that when delta t changed, n also changed. They are related. So here, my a, right, is my starting point of what I'm looking for in my independent values. So my a is 0, and my b is 10, okay? And it turns out that the relationship between all of these variables is that b minus a divided by n equals delta t, and that b minus a divided by delta t equals n. Okay, so those are both true. So if delta t gets smaller, if this number gets smaller, that means that n had to get bigger, right? So these are directly related, okay? So now that we have this sort of process of how we can approximate from a table, let's see how we sort of retrofit that if we were to have a graph, right? Another scenario that's completely plausible based on the work that you're doing, okay? So here we have a figure that shows the velocity of an object over 31 minutes, okay? So here we have a picture. We see that it's a curve. Unfortunately, if it was a triangle, right, we could get the exact area to answer our questions, but we can't do that because it's a curve. So here we want to estimate the total distance traveled by whatever this figure is by using a left-hand sum with n equals 2. Okay. We also want to estimate the total distance traveled using a right-hand sum with n equals 2. So I want you to think about what n represents, how we might then use our sort of rectangles that we talked about before to fit those in, and what a left-hand sum and a right-hand sum, what the difference would be when you draw in those rectangles. Okay. So I'd like you to take 2 minutes, see if you can figure out how we might approach this, and then we'll go through it together. So try a couple things out. Feel free to check in with someone next to you if there's someone there, and then we'll go through it together. Okay, take about 30 more seconds. Okay. So here for both of these, n equals 2, which means that we are using 2 rectangles. So what we want to do to try to figure out how to separate these rectangles is we need to do some calculations about the relationships. So we said that here that b minus a over n will give us our delta t. So in this picture, in this scenario, we are looking at what happens over 31 minutes. So from 0 to 31. So those are the endpoints here. A is 0 and B equals 31. Okay, so we're going to do 31 minus 0 divided by 2, because for both of these, n equals 2. So here, when we divide that in half, we're going to get 15.5. So my delta t is 15.5. So that means I want to look on here and try to figure out roughly where that is in my picture and label it. So 2, 4, so 15 is here. So 15.5 is like right by 15. So I'm just going to pick a dot that looks like where it is, and I'm going to label it so I remember. Okay. So 15.5 is my delta t. So now I'm going to do part A, which is a left-hand sum. So that means I need a rectangle that goes from 0 to 15.5 and touches my graph with the left-hand corner of my rectangle. So at time equals 0, I want to go up to that height, which appears to be 20, and I'm going to remain constant until 15.5. Okay. So my first rectangle looks like this. And if I'm thinking about the area, remember we're going to be adding up the different areas, I'm going to need to multiply the height by the width. So I'm going to do 20 times 15.5, and this is going to give me an area of 310. So again, 20 times 15.5 is 310. And then for my second rectangle, I go to 15.5. I go up until I hit the rectangle. That's going to become my constant. And that goes all the way until this 31 mark. Okay, so again, I'm just sort of eyeballing this height because I don't have a great way to get it exactly 15.5, and I don't have the algebraic function. So I'm approximating here. Okay, so it's a little bit above 15. I'm going to call it 17. You may have called it 16, but it's right around there. So this height, 17 times my width of 15.5. So that's my second rectangle. So 17 times 15.5 is going to give me 263.5. And I'm going to add those together to get my left-hand approximation, right? So I'm adding up all the different areas. So that's 573.5. So my n equals 2. This is my first rectangle. This is my second. For each one, I'm doing height times width. And that is what allows me to get my approximation for my left-hand estimation. Now, I also, for part B, want to do this with a right-hand approximation. And so that means for each rectangle, I'm picking the point on the right. So for my first interval, 0 to 15.5, I want to use the height of the value when I do 15.5. So I already approximated that height to be 17. So 17 times 15.5. We said was 263.5. And then my second rectangle, I use the right-hand height, which happens to be at 0. Right? So now I have 0 times 15.5, which is 0. I add those up. And I get 263.5. Okay, so I'm just going to shade in this red part to sort of highlight the difference here. So what I want to point out here again is that my left-hand estimate in this case, right, the blue one, was my overestimate because it's bigger. And my right-hand approximation is my underestimate here because it's the smaller estimate. Okay, so that's how we start to look at and approximate using these rectangles on a graph. So again, you want to start by figuring out your delta t, label it, and then when you do a left-hand approximation, you use the leftmost point of each interval to get your height. When you do a right-hand approximation, you use the rightmost value for each interval to get your height, and then you draw that constant line, and you find the area of each rectangle, and you add them up. Okay? Now, another type that we're going to encounter, so we've done a table, we've done a graph. What if we actually have a function, right? An algebraic function. So if t is in hours of a 20-hour period, the rate at which bacteria population growing is given by f of t equals 3 plus 0.1 t squared. Find an over and under estimate of the total change in bacteria over this period if delta t equals 4. So we know something about delta t. We also know something about the length of the interval. And so what we need to do here in order to actually solve this is we need to set up our own table. Okay, so just like we did in the first table example, we need to have the values of the rate so we can do left and right hand approximations. So if delta t equals 4, that means that we are counting by 4s. And since we know it's a 20-hour period, that means we're going from 0 to 20 and that we're counting by 4s. So 0, 4, 8, 12, 16, 20. Okay, so again, I have the length of the interval and I know my delta t. That allows me to generate my independent values that I want to use. Now, I'm going to need to plug each of these values into my function to get the corresponding rates. Once I have those rates, then I can do my left and right hand approximation. So that's what I'm going to have you try. So you're going to plug each one of them into this function to get the corresponding rate. Then you'll do a left hand and a right hand estimation and use that to find the best estimation for this particular model. If you have time, also jot down what is your N, what is your A, and what is your B. Okay, so take 2 to 3 minutes to work that out, and then we will go through it together. Okay, so take about 30 more seconds. All right. So again, we have to plug each of these t values into our function to get the rate for that particular time. That's going to help us generate this table. Once we do that, then we can do our left and right hand approximations. So again, rate times time. Each of our time intervals is 4 hours. So here this was in hours. So here for our left, we're always going to pick the left hand rate. So 3 times 4 plus 4.6 times 4 plus 9.4 times 4 plus 17.4 times 4 plus 28.6 times 4. So again, we're not going to use the rightmost rate when we do our left-hand estimation. And when I plug that in, I got 252. And I multiplied those out and added them up. And then for our right-hand estimation, we're going to do the same thing, but we're going to be picking the rate on the right. So here now we're going to have 4.6 times 4 plus 9.4 times 4 plus 17.4 times 4, 28.6 times 4 plus 43 times 4. So when I added those all up, I got 412. And so my best estimate is going to be to average those together. I'm going to put that up here. So my best estimate will be 252 plus 412 divided by 2, and I get 332. Okay, so again, the 332 refers to the total change in bacteria. So I have an increase of 332 bacteria over this given time. That's my approximation of the change. Okay. So left, right, best. Now we know our delta T equals 4. That was given in the problem. A and B, those are your endpoints of your independent values. So that's 0 and 20. And then your N is the number of intervals that you're using to approximate. There's 2 ways to figure this out. We can use B minus A divided by delta T. So since we have all those values, or we can count. So that's one interval from time 0 to time 4, 2, 3, 4, 5. Okay, we would have gotten the same thing if we had used the calculation. So 20 minus 0 divided by 4 also gives me N equals 5. Okay, so if you are asked to approximate the total change of the original function and you are given the rate formula, you have to generate your own table based on you'll either be given delta t or n, right? If you're given n, you can use the formula to find n. So one of the things that I think is going to be important here is the words total. Total change is sort of the key words that we're looking for that tell us that this is the type of process we're doing. So if you see the word total, that's an indicator that we are talking about approximating the area under the curve. Okay. The next part I'm not going to do because we're not going to have enough time to finish it. So I'm 99% confident that this is not on your quiz, but I will double check to make sure. And we will pick up and do that last example next time we meet. Okay. So have a good rest of your day. I will send you a follow-up email tomorrow with a reminder about the Monday's quiz. And also as a reminder, there is the review tonight at 5 with William.